All right, so I'm Andy Kaylor. I wanted to start out by mentioning I put my email address on here, but unlike most speakers here, my email address does not reflect company affiliation. I am currently an independent contributor to LLVM. So I'm going to talk about fast math. I don't know how much to assume about what you know about fast math. So I am starting from the perspective of looking at both the good and the bad. If you already think that fast math is dangerous, then you can kind of tune out the part where I'm explaining that. And if you already think it's useful, then maybe you can look at your phone while I'm explaining why I think it's useful. But if you don't already think that it's both dangerous and useful, then I hope you'll hear me out. And if you do already think that it's both dangerous and useful, then hopefully what I get to at the end will have some usefulness in terms of how to make it better than it currently is. So to start out with, the bad, this is just an overview of a few things. One of my favorite things from the old GCC documentation for the -f fast math option is the documentation used to say that this option would either make your program faster or die trying. So the die trying part, I guess, is the problem with this option. Recently, we had a discussion on the LLVM discourse about deprecating OFAST. And there, John Chesterton suggested that OFAST means make it faster and wronger, please. Now, I don't know what his intention was, but I think that this is a good interpretation of OFAST and fast math in general. And making it wronger seems like something you wouldn't want to do, but I think in the case of fast math, that is the intention. And I'll explain why that might be okay and why it might not be. But in general, and then the last thing I have here is a link to a blog post that Simon Byrne wrote a few years ago that goes into the issues. So I think this is really good, and I wanted to include it as a reference. I've heard it suggested that fast math is a foot gun. And I want to suggest that it's actually much worse than that. Fast math is a case where you're giving the compiler a gun and asking the compiler to decide when to shoot you in the foot. And it will. So I wanted to go over some of the problems with fast math. Fast math will almost certainly change the numeric results of your program. A typical example here showing reassociation. This is doing just basic algebra 1 kind of changing around of an operation, but with floating point math, this is going to give you a different result in a lot of cases. And this is the basic, most fundamental thing that happens all over the place. Even if we don't find optimization opportunities, we're likely to do things like this just to canonicalize the input. The next thing I have here is that fast math will optimize away explicit checks for nans and infinities. Now, I should mention here, I'm talking about fast math as if it were a monolithic thing. If you're familiar with the IR representation of this, we have like 6 different flags that control different behaviors. But specifically, the no nans and no infinities, which are put on if you use -f fast math, this will optimize away explicit checks for nan and explicit checks for infinity. And so even if you think, I wrote my code and I know I handled the nan case and then I did the things, and so you can optimize the things that don't have nan, and I'll have already checked for that, but we optimized away your check, so it wasn't helpful. The next thing, as Joshua mentioned, in a lot of cases, when we're using fast math, we'll automatically turn on the flush to 0 and denormals are 0 bits. And so even though you might not be aware that you signed up for this, you'll suddenly stop getting denormals in your calculations. And when you get down into the value range, suddenly everything goes to 0, and nothing told you why that happened. And then lastly, fast math can lead to a complete loss of precision, depending on what your algorithm is and how sensitive it is to things. We can potentially get rid of your result and essentially turn your algorithm into a random number generator. This is an example I have where if you have A and B are relatively large values and you're subtracting them, and then you want to add some epsilon term to keep track of running error, for instance, we might reassociate this, and the epsilon, because it's off scale from A, gets discarded completely, and suddenly your program is not doing what you wanted. So to wrap this section up, I wanted to give the worst case example. This is something I actually came across recently. This is from a classic algorithm that is trying to programmatically detect the mantissa and machine epsilon. And it's doing that by looking for the smallest value of the form 2 to the k for which a plus 1 minus a is not equal to 1. So it's doing this in a loop, trying to find the limit where that has gone over. And so if you look at this, take a second and see what kind of IR do you think we're going to produce after optimizing this with fast math enabled. If you guessed that we're going to eliminate it completely, congratulations. So what happened here is we look at this, and we have this C equals A plus 1 minus A, and the optimizer looks at this, sees that reassociation is enabled, and so it says, oh, I can get rid of that A minus A term, and you just get C equals 1, and this becomes an infinite loop. And infinite loop is undefined behavior, so we got rid of it for you. So that's the bad of fast math. So the question is, why would anyone ever use this if it's doing these nasty things? And the answer is that this is really useful for optimization. It, as the name would imply, it makes your program faster. A simple case of this is reassociation. If you have written your code in such a way that you have something inside a loop that we figure out in the optimizer, we could hoist part of it out if we just had things in a different order, then we can do that. So in this case, you have A sub I equals X times B sub I times Y. We can reassociate that, take the X times Y out, and you're likely to get very nearly the same answer you would have, but in a shorter amount of calculations. The next thing is vectorization. This is something that comes up pretty often. If you're vectorizing a loop like this with integers, no problem. The integers don't have this sort of reassociation problem, and so you can vectorize this loop and do the calculations. But if you're using floating point values here, you can only vectorize a simple loop like this with reassociation enabled. So it's an important case. And then finally, if you know that you aren't going to have nans or infinite values in your program, indicating that to the compiler can turn off some restrictions and enable optimizations that are normally completely valid, but become invalid if you have nan. So for instance, x minus x equals 0. If x is a nan, you can't do this, but if you know that x won't be a nan, then you can make that optimization. So how do we make this more useful? I want to start out with, a lot of this in terms of command line options. I'm going to be showing a Clang bias here, but these same sorts of reasoning can apply to other front ends. I don't know what other front ends might do, so I'm going to talk about it from the perspective of Clang and what Clang offers. First, the basic idea of fast math and the fundamental options were inherited from GCC. And GCC has these two options, -f fast math and -f unsafe math optimizations. The problem with these two options, in my view, is which one sounds like it's going to be riskier? Do you want fast optimizations or do you want unsafe optimizations? Yeah, obviously you're going to want fast, right? But the fact is, the main difference between them is that the unsafe optimizations doesn't make the assumption of no nans and no infinities. And so fast math is actually much less safe than unsafe. So in the great tradition of, there are many, many options that you have for controlling floating point behavior, and it's hard to keep them all straight. So we added another one. And one more option here. In Clang, we have this option -f FP model, and this can be, let you set what we think are the broad categories of behavior you want. So we used to have just fast, strict, and precise, where that determined whether you wanted to enable fast math, whether you wanted value-safe optimizations only, or whether you needed full exception semantics and everything. But recently, we've added a new option, aggressive, and separated that from fast. So now if you do FP model fast, you get something like the F unsafe optimizations. And if you want to push a little further, then you can use aggressive and get what fast used to do, which is mostly equivalent to fast math with a few extra things. And finally, there are many individual options that let you turn things off. And this is useful because some of these things, like if you're not checking the error no value, you should really be using the F no math error no, because that lets us do optimizations on the math library functions that we couldn't if we have to correctly maintain error no. Other things, you can turn individual things on and off. FP contract is pretty safe. This enables FMA, and FMA, broadly speaking, is more accurate than the answer that you would get from separate math, multiply and add operations for the inputs you have. Sometimes separate operations will kind of mask errors in the input values and make it look like you got the answer you wanted, but it's actually more accurate to do it as a fused operation. And so unless you want that masking or you want binary exact results, then turning that on is good. And in fact, the C language standard enables doing fusing of operations as long as they occur in a single expression. So I've noted here we've got on, off, and fast. And the difference between on and fast is whether we will fuse things that are in different expressions in the source. And so you can control things for a compilation unit like that. Then we have pragmas that let you locally control things. So if you know where you want to turn off the fast math just within a particular part of your program, you can do that with various pragmas. And again, I would encourage other language implementations to add things like this because it makes fast math more controllable and lets you rein it in. So as a general approach, what I would suggest as a general approach is if you want to see how much you can get out of fast math, is you compile everything with FP model fast, test to see are the results within the acceptable range. And if they aren't, then you have to go through and for each file that you're compiling, turn it off in various places, see where the problem it is. Then once you've isolated the file in which your problems are being introduced, you can re-enable it with pragmas and use that to narrow in on local scopes. But this is really kind of a difficult thing to do. It's a very labor-intensive process and easy to get lost in the weeds when you're trying to do this. So what else can the compiler do to help with this? This is kind of a long-term dream that I have, and this is the RFC portion of my talk. What I would like to see is I would like to introduce something in the optimizer itself, where we would, every time we wanted to perform a fast math transformation, do something to ask permission. So I'm viewing this as conceptually similar to the op bisect option, where you can set a limit and say, okay, do fast math optimizations till you get here, and then stop, and it would print out output that would say, okay, I did this, and then when you get to the limit, it would say, I wanted to do this, but it was disallowed. And I'm envisioning this as something that we would expose to users, and users would be able to see, okay, when I hit this optimization, that's where my program broke. And use that to go back to automating this kind of general approach. Ideally, I would like for this to have been something that in the way that in the optimizer, where we're checking to see if the fast math flags are enabled, I would like this to have been kind of part of the gatekeeping for that, but I don't think that's practical. The way that we do it is, sometimes it happens in pattern matching. Sometimes we check it in a function before we call another function to do optimizations. Things are just not split up in a way that makes this really practical. So the best I've been able to come up with is just you do all your checking, you see that the fast math semantics enable a certain optimization, and then just before doing it, you would call this. And so here's an example taken from the current LLVM code where we're doing the transformation, and we've checked that the instruction has allow reassociation, and we're about to do it. Joshua mentioned in his talk that a lot of our checks are wrong, and this is one of them because there are two operations that are being reassociated here, and we're only checking the flags on one of them. So as we're fixing that kind of thing, my suggestion is that we would go in, add the extra has allow reassociation so that we're checking in all the operations, which, by the way, the reason I think we got into this state is people imagine this is going to be monolithic. You have fast math either turned on for your whole program or turned off, and that doesn't work well with the technique I'm suggesting of disabling it in selective places and whittling down. So you can get into this case where you have mixed operations with different flags. But so we fix the flags and then simply add in, before we do the transformation, add a check. Say, should we allow fast math optimization on this? And then this would print, I'm imagining based on debug information and various things. I picture it printing out a message saying that we allowed the fast math optimization and giving you optionally the IR that enabled it. And so this would help us to find the problems where we have done the checks wrong and also let users see what we're doing. And then the user can use this and say, okay, I didn't mean for that to happen. I need to turn that off there. So a lot of work to make that happen, but that is my suggestion. And that's what I have. So.
Okay, we have a microphone here, and on this side, I can run the microphone to you. Go ahead.
So when the warning about using nan and inf landed upstream, I did some cleanup on our internal code base to fix places where people were trying to use nan and inf with fast math enabled. And one of the things I did was try to narrow down which parts of it were important for them. And I guess as part of doing that, I was like, almost all the cases, performance only actually mattered for reassociation and signed zeros, and everything else is completely irrelevant. And I thought that was sort of an interesting result that, what I would like to see is a way for the compiler to tell the users that, hey, if you reassociated this yourself, maybe you wouldn't need to set any flags or something like that. I don't know if that's viable. Some way of instead of even having this flag, if we could eliminate fast math by telling the users, like, hey, if you change your code a little bit, like, then you'll get the desired semantics without having to set this globally affecting, flag. I don't know, is that something you've thought about?
So I think that that would be useful, and something like I'm suggesting here with the allow check, we could possibly refactor that to make it a optimization remark where we say, we saw this opportunity, but we couldn't do it because we didn't have this. As far as the user fixing it in their code, in a lot of cases, I think that's reasonable in what you would want as a user. But there are also places where in the code things aren't together, but then after a chain of optimizations, we bring things together, and that exposes the reassociation opportunity.
Yeah.
So I don't think that you can.
I don't have any intuition.
Necessarily do everything.
Like I haven't explored that, but I don't have any intuition about like how often one or the other happens. So just as like naively, it seems like it would be nice if this is possible to explore, and like if we could find out that in fact like most of the cases that actually matter, just changing the code a little bit, or like the sum case, right, where you have a loop adding up all the things. Like we have in C++ now, the like parallel algorithms or whatever, where you could actually just specify call like I don't care, right, and like that could just automatically set reassociation, and then users never have to worry about it.
Yeah, that is a good point for because a case like that, you really with just plain C semantics, you can't. There's no good way to say go ahead and vectorize this loop, but like OpenMP has the ability, and that raises a question when you use OpenMP and say SIMD on this loop. Does that mean that you are explicitly giving the permission to use reassociation? I think that we probably should interpret it that way. But yeah, there are definitely things that could be done.
So we very nearly have a class already in LLVM that can kind of do this bottom part that you're imagining, right? So there's optimization remark emitter that can, it basically on the front end we expect front ends to kind of emit a minimum level of debug info. That way they can match up like source and line info. The issue is the ergonomics of it are kind of bad. In Clang, you would say -R pass -mist equals, and then an LLVM specific pass name, which like as an end user of the compiler, like I have no idea what pass did that transform. Is that inst combine? Is that selection dag ICEL? I don't know. But even as someone working on LLVM who's writing passes like that, I'm just, boom, I wrote the optimization. Oh, I forgot about updating the debug info, and oops, I didn't insert optimization remarks about, we did this transform or we didn't do this transform. But it might be very helpful to say R pass mist equals floating point reassociation, and then have the compiler spit out a bunch of things like this saying, because, I did not do this transform because you did not enable -F reassociation or whatever, right, kind of thing.
Yeah, and so you could do this, with optremarks, and I'd like to see at least, the basic framework leverage that.
You also kind of mentioned,
but I want to have a gatekeeping feature where it will automate the process.
You also mentioned like kind of finding things. So optimization fuel is like a generic term, I think, for like how many times you perform a transform, and that helps you bisect like when you do a transform many times, which one introduced a problematic change. So maybe that's something that can kind of get mixed in. I think we have that for some passes, but not a generic functionality. Like CLOpt maybe controls that. Okay. And then another question too is, we want to build a libc for LLVM that's very, very precise. And the trade-off there is like, again, we're going to have potentially users that they really care about fast math, and they're in that camp firmly of like, I don't care about precise results. Is there a way to detect at runtime? Has someone set fast math? Is that a terrible idea for libraries to do that kind of thing?
I think you should ask the next speaker.
Okay, the next. Okay.
Yeah. So being able to like choose different implementations of the math library based on what your fast math is, I think a very useful thing if we could.
And then the pragmas are a nice way to chop it down. Maybe statement attributes could be used to say like, I'm calling sign here, like I don't care about here number.
Yeah.
Thank you.
Sure.
Hi. So I have a question. So you mentioned that you're going to instrument this in all the places where the transformations are going to happen. Is that how?
That's what I'm proposing, yeah.
Okay, so like, how do you plan to maintain it? Like, because there will be more optimizations coming in, So how do you? And that's one. And the second thing is, this is, you're trying to do it for the debug information purpose, right? So now this code is instrumented all the time. So now if you're putting it all around the code, so what about the readability? So like, and do you want it to be in a release build of a, the library?
Do I want it what?
Like in a release build, do you want to have this instrumented code? Like this is more like an instrumentation, right? Like you're adding this check before the optimization is done. So if I don't want this in my actual, build of the library, how do I get rid of it? So like a couple of questions, right?
Yeah, so for that last question, I think, what we do with op bisect, we do this, on every pass that we run, we call a gatekeeping function. And if you haven't used the option to enable that, it just always returns true. And that's kind of what I would imagine here. So hopefully that would be a very fast thing. And,
Or maybe
if that's
them
still...
inline, or maybe making them like always inline kind of thing. Like.
Yeah, I mean, I don't know if it would have a big enough impact. We could potentially add a way to have it automatically optimized out. To when you build the compiler, say build without this, and it would make it a no op.
First question where like, how do you plan to maintain?
I'm sorry to cut you off, but we are running over time.
Yeah, so maintaining it, that is the big problem with this. Is like I said, I'd like to have it built into the check for the flags, but I couldn't find a way to do that scalably, and so really code reviews would be the only way to maintain it.
Okay, thank you, Andy. And